Okay, good morning, everyone. Thank you for making it for the first talk of the day. So, one problem that I think all of us are familiar with is that to correctly migrate seismic data, we require an accurate velocity model. So accurate in this context means that the travel times that we predict match those of the observed data. And what we find is that when we have an inaccurate velocity model, the images that we compute are defocused and incoherent. The subject of my presentation today will be least squares migration in the presence of velocity errors, and what we'll propose is a modification, or a method rather, that allows us to use an incorrect velocity to compute images with features that are similar to those computed for the correct velocity. So let me start with an example to show you exactly what I mean. Shown here are two subsets of least squares migration images computed for two different velocity models. So the field data that I'm working with here are provided courtesy of any, and the image on the left was computed using the velocity model that was provided along with the field data. In comparison, the image on the right was computed using what I'm calling the simple velocity, which in fact is a laterally invariant velocity model, so a simple V of z model. And so we can safely assume here that the provided velocity is more accurate than my simple velocity, and therefore that the structures that we see on the image on the left are more representative of the true subsurface as opposed to the structures we see on the image on the right. So now pay attention to the image on the right now as I compare the conventional least squares image to the image that we obtain with our method, still using the simple laterally invariant velocity. So now if we compare these two images on the screen, we see the same features in both images, despite the fact that they were computed using different velocity models. But of course these features, the corresponding features in both images are located at different positions in depth because they were computed with different velocities. So we'll come back to this field data example in detail later, but let me go through a little theory to try to explain exactly what I'm doing differently here from conventional least squares migration. So for the examples shown here and in the report, I'm working with constant density acoustics described by the wave equation shown here. In this equation, C naught is a smooth velocity field. If C naught is smooth, then U naught is an incident wave field that does not contain any scattered waves, and this incident wave field U naught is computed for a source function F. We can write a similar equation for the scattered wave field U1, the singly scattered wave field U1. And in this equation, C naught again is the smooth velocity, U1 is the scattered wave field, and M now is the reflectivity image that we seek to invert for. When we synthesize data by solving this equation, it's commonly referred to as Born modeling. And this is a linearized equation because U1 is linear in the reflectivity M. So with that in mind, let me switch notation here to this matrix vector notation. In this equation now, M is the discretized reflectivity image. L is a linearized forward modeling operator, which involves the solution of the two previous wave equations, one for the incident wave field, another for the scattered. And in addition, L also includes a sampling or a restriction operator that restricts the wave field to locations where we have seismic data, D. L is commonly referred to as a demigration operator because it maps from the image to the data as opposed to a migration operator which maps from data to image. And so the transpose of a linearized forward modeling operator is in fact a migration operator. In this case, L transpose applied to the observed data D with a subscript O gives the what I'm calling here the RTM image, the reverse time migration image. Of course, in practice, most implementations of RTM are much more complicated than this, but I just want to be clear that for the images that I'm calling RTM in this presentation, I'm computing with just a simple single application of L transpose. But instead of computing an image with just L transpose, we can obtain a better image with the least squares solution as shown here. So in this equation, we can see that the least squares image is related to the RTM image, which is given by L transpose D by the inverse Hessian. So for example, if the inverse Hessian is the identity, then we'd expect the RTM image to be the same as the least squares image. But in most cases, the Hessian, of course, is not the identity. To solve this equation, we typically can't afford to compute or sometimes even store the inverse Hessian. So what we do instead is we pursue an iterative solution by solving this optimization problem in which we're trying to minimize, with respect to the reflectivity model M, the difference between predicted and observed data being given by LM and observed data D. And we solve this typically with just conjugate gradient iterations, for example. So let's look at a synthetic example here. So here's the true velocity, which is a smooth version of the Marmousi model. And now here's the RTM image, the reverse time migration image computed for the true velocity. I'll just remind you here that this image was computed with just a simple application of L transpose. And we can begin to see the features of Marmousi in this image, but in this image the amplitudes are not well balanced. So for example, the amplitude of the reflectivity tends to be larger at shallow depth compared to greater depth, and the image is also not well focused, especially at greater depths. In comparison, here's the least squares image, and now we see amplitudes are well balanced, and reflectors are also better focused if I compare to the RTM image. Let's look at the same comparison now for a field data example. This is the same field data that we saw a little bit earlier, and we'll go into more detail later, but here just let me show the images we obtained. So here's the provided velocity model that I'm using for migration. Here's the RTM image computed with that provided velocity model, and now here's the least squares image. So let me toggle back and forth. Here's RTM, and here's least squares. So the comparison here isn't quite as dramatic as the Marmousi example, but the frequency content of these data are quite different, and also the maximum source receiver offset is smaller in this case compared to Marmousi. But in any case, we can make the same comparison, which is that the least squares migration image has better balanced amplitudes and also better focused reflectors compared to RTM. So now returning to our equation for least squares migration, in solving this optimization problem, it's assumed that the velocity is correct. So I'll remind you here that M here is the reflectivity image, so in solving for the reflectivity, nowhere do we ever change velocity. And since we're assuming that the velocity is correct, what we find in practice is that when the velocity is incorrect, the images that we obtain are defocused and incoherent. With the method that we propose now, we'll show that we can use, by solving this slightly different optimization problem, we can obtain images with the same features as those computed for a more accurate velocity. So the main difference here is that I've introduced a time shift operator T that's applied to the observed data D. And this time shift operator, in fact, is simply a sync interpolation operator. And the action of this time shift operator is to shift the observed data so that its travel times match those of the predicted data. So then if the predicted and the shifted observed data have the same travel times, then their difference will quantify mostly differences in amplitude. So for this reason, I call this method amplitude-only least squares migration, and I'll call the images that we obtain with this method amplitude-only images. Okay, so the first test we want to do is just to see what happens when we have the correct velocity, or the true velocity for migration, because as we said, the time shift operator acts to match the travel times of predicted and observed data, and if we have the correct velocity, we expect the travel times of predicted and observed data to already be the same. So for the true velocity, here's the least squares image that you saw earlier, and now here's the amplitude-only image. And if I toggle between the two, these images are very similar, except near the edges of the survey where we lack data. So now let's see what happens when we have a wrong velocity. So here's the incorrect velocity model, and the difference between this velocity and the true velocity is the velocity error shown here. And so what you want to notice here is we have both positive and negative anomalies, and what's more, these errors in velocity are quite large, with the maximum error being about half a kilometer per second. And I'll just draw your attention to the negative anomaly at 4 kilometers and the positive anomaly at 6 kilometers. And we're going to see the effects of these on the images in a few slides. So here's least squares migration for the wrong velocity model. And now if I compare this to the amplitude-only image, we can see an improvement in illumination, and also an improvement in focusing and continuity of reflectors. And what's more, if I compare this to the least squares image computed for the correct velocity, we can see the same features in both images, except the features in the amplitude-only image are shifted with respect to the features for the image computed in the correct velocity. And actually we can see, for example, at 4 kilometers, the reflector shifts up with respect to this image for the correct velocity, whereas at 6 kilometers, the reflectors tend to shift down. And this is just a reflection of the velocity errors that we have. Okay, so now moving on to the field data example. These data, as I mentioned before, were provided courtesy of any. These are marine streamer data, and the entire data set consists of more shots than what's listed here, but I'm just migrating a subset of the shots that, which consists of 431 shots with 25-meter shot spacing, and then each shot has 99 receivers with a 12.5-meter receiver spacing. This corresponds to a maximum receiver offset of about 1.2 kilometers. The data as they were provided to me were regularized and multiples were attenuated. And in addition to that, I just did a simple bandpass filtering to just limit the frequency content of the data. These are field data, of course, so we need to estimate a source function. Shown on the left is a normalized amplitude spectrum of the recorded data. This is the spectrum after smoothing and after applying the bandpass filter that I just mentioned. On the right, the black curve shows a zero-phase wavelet, which corresponds to the amplitude spectrum on the left. And then just for comparison, the red curve is the wavelet computed by simply stacking the water bottom reflection. And this is just a kind of QC to show that we're doing something reasonable by using zero-phase wavelet computed from the amplitude spectrum here. Here's the provided velocity model that you saw earlier. Here's the RTM image again, and comparing this to least squares migration. And then, so now what we want to do is see when we have what happens when we have a velocity model that's clearly incorrect. So in this case, here's my simple velocity that I'm using. This is a laterally invariant velocity model, except near the water bottom, where I assumed I know the water bottom geometry. And the difference between the simple velocity and the provided velocity is shown here. So this is kind of analogous to the velocity error in the previous example, except we don't know the true velocity, of course, in this case. And so we'll see larger errors more or less on the left side of the model, and this is where we expect to see differences in the images later on. So here's least squares migration for the simple velocity. And now let me compare this to least squares migration for the provided velocity, which is more accurate. We assume is more accurate than the simple velocity. Now, if you compare these two images, the most noticeable change is probably that reflectors are shifting relative to each other. But also we see that in the image computed for the simple velocity, reflectors are less focused and less coherent. And this is, of course, due to the fact that we're using a worse velocity model for migration. So if I zoom into those areas enclosed by the yellow boxes, these are the slides I showed at the beginning, we can see these images are quite different, and of course it's just a reflection of the fact that we're using the wrong velocity. So now let's see what happens when we use amplitude-only migration. So here's the least squares migration for the simple velocity, and now here's the amplitude-only migration. And so the first thing you might notice is that reflectors are not shifting so much. So this means that the reflectors are still misplaced in the case of amplitude-only migration. But now if we compare this to least squares migration for the correct velocity, so here's amplitude-only migration for the simple velocity, least squares for the correct velocity, or the provided velocity rather. We see the same features in both images, but these features are shifted with respect to each other in the two cases. And now zooming in again on the area enclosed in the yellow boxes. On the left is least squares for the provided velocity. On the right is amplitude only for the simple velocity. And now we see the same features in both images, but these features differ in depth. We're computing these images by minimizing essentially a data domain misfit function. So we need to look at the data that we compute. So here I'm going to show data computed for two different source locations. The first located at 1.9 kilometers. So on the left here I'm showing the data after migration, and these are predicted using the simple velocity model in addition to the computed amplitude-only image using Born modeling. On the right I'm showing the observed data, and here I've just mirrored the data so it's a little easier to compare. And so let me just point out some similarities for you. So for example, we can see this kind of a low amplitude notch that we've predicted in the data on the left. There's also this small bifurcation, which we can see in both data sets. But if you look closely, you'll notice that the events in these data occur at different travel times. So it's really easy to see this with just the near offsets. So you can clearly see in the zero offset traces the shift, the travel time shift between predicted and observed data. And this is just simply reflecting the fact that we're minimizing the difference between predicted and shifted observed data. So there's no guarantee at all that we're going to match the travel times of the observed data after this amplitude-only migration. And if we go ahead and compute the time shifts, this is what we find. And in fact, these time shifts exceed 1/2 period. So I'd like to step back briefly here and just say a little bit about the method that we're using to estimate these time shifts, because it turns out to be very important, especially in the case of field data. So we're using here dynamic image warping to estimate time shifts. And so if you're not familiar with dynamic image warping, all you need to know for our purposes is that it's a method for estimating shifts between two sequences or two images in this case. And it allows us to constrain how rapidly the shifts change. So it allows us to constrain the derivatives of shift. In this case, I'm using a 3D warping, so that means I'm constraining the derivatives of the shift in all three directions. So in position, which refers to shot position, offset, which is receiver offset, and then time, obviously. And then just for comparison, let me show you what happens if we were to use a 1D warping. So here's what happens when you try to estimate these shifts using 1D image warping. And now these shifts are still constrained in the time direction, so they're smooth in time, but they're no longer smooth in offset or position. And in fact, if you were to try to use these shifts in migration, you would see essentially artifacts in the image which are due to the inaccuracy of these shifts because we used this 1D warping as opposed to 3D warping. Okay, so going now to the second shot position. So here we're going to look at data computed for a shot at 5.6 kilometers. On the left again is predicted data, on the right is observed. And so here, for example, you can see this event that we've predicted on the data on the left. But now these travel times in this case are closer, right? And this is expected because the shot position that we're looking at is above the area where there's not much velocity error. So when we don't have velocity error, we expect there to be no changes or small differences in travel time between predicted and observed data. And in fact, that's what we see here. The travel time shifts between these data are much smaller than in the previous case. So the final example I'll leave you with is I kind of focused on applications where the velocity model clearly is wrong. But in this case, this is the provided velocity model. We of course don't know if this is the best velocity, the correct velocity either. So it's interesting to see what happens when we try to use amplitude-only migration in the case where I'm using the best velocity available to me, which was the provided velocity. So here's the least squares image now, and here's the amplitude-only image. So least squares, amplitude-only. And for example, you could look at the reflectors in between 3 and 4 kilometers. And we see that these reflectors tend to move up in the amplitude-only image. So this might be suggesting that we have a low velocity anomaly in that area. So in summary, we've proposed a method for migration by minimizing what I called an amplitude misfit, which is just simply the difference between predicted and shifted observed data. We saw that this amplitude misfit results in improved images when the velocity is wrong. And in fact, we expect to see more improvement when we have longer offsets. This isn't something that I demonstrated directly, but in fact, we're relying really on offset information to give us information about the inconsistencies in the model. And so if we have longer offsets, we have more information at our disposal. One thing that's worth mentioning is that this can easily be extended to other wave equations, so there's nothing specific about the acoustic wave equation that I'm using here, and you can try the same approach with, for example, an acoustic anisotropic wave equation. And then finally, we saw that the depths of reflectors in these images are still incorrect if the velocity is incorrect. So we need to correct these depths. One possible way to do this is to register the image with well logs if we have some well logs in the area, and then interpolating those shifts to create shifts for an entire image, and that way correct depths for an entire image. And with that, thank you for your attention. I'd be happy to take questions.